Imagine shining a beam of light at a screen with two narrow slits. Behind the screen is a wall that captures the light passing through. You might expect two bright lines on the wall, one behind each slit. This is what classical physics predicts. However, the quantum world behaves differently. Instead of two lines, we see an interference pattern. This pattern consists of multiple light and dark bands, even when we send single photons one at a time. This suggests each photon somehow passes through both slits simultaneously, interfering with itself. This strange phenomenon is called wave-particle duality. The two-slit experiment reveals a fundamental mystery. Quantum objects like photons or electrons don't behave like everyday objects. They exist in a superposition of states, being in multiple places at once until measured. This challenges our classical intuition and forces us to rethink the nature of reality. The two-slit experiment highlights a crucial issue in quantum mechanics, the measurement problem. Before measurement, a quantum object exists in a superposition of states, described by a mathematical function called the wave function. This wave function evolves deterministically, governed by Schrödinger's equation. However, upon measurement, the wave function appears to collapse. The quantum object randomly chooses one definite state from the superposition. This transition from a blurry superposition to a sharp, definite outcome is not well understood. The measurement problem asks, what constitutes a measurement? How does the wave function collapse? And what determines the specific outcome we observe? These questions have puzzled physicists for decades and lie at the heart of different interpretations of quantum mechanics. The Copenhagen Interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, is the most widely accepted view of quantum mechanics. It argues that the wave function doesn't represent a real physical wave. Instead, it reflects our knowledge about the quantum system. According to the Copenhagen Interpretation, the act of measurement forces the quantum system to transition from a superposition to a definite state. This collapse is random and probabilistic, governed by the Born rule. We cannot know which outcome will occur before the measurement. The Copenhagen Interpretation emphasizes the role of the observer and the limitations of our knowledge. It suggests that we cannot know everything about a quantum system with absolute certainty. Instead, we must embrace the inherent uncertainty and probabilistic nature of the quantum world. Section 4. Many worlds, a universe of possibilities. The many worlds interpretation, proposed by Hugh Everett III in 1957, offers a radical alternative to the Copenhagen view. It suggests that the wave function never collapses. Instead, every possible outcome of a measurement is realized in a separate, parallel universe. In this view, when we perform a measurement, the universe splits into multiple copies. Each copy represents a different outcome. We experience only one outcome, but other versions of ourselves exist in these parallel universes, each observing a different result. The many worlds interpretation eliminates the need for wave function collapse and preserves the deterministic evolution of the Schrödinger equation. However, it introduces the mind-boggling concept of an ever-expanding multiverse, where countless parallel realities exist alongside our own. Section 5. The pilot wave guiding the quantum world. The pilot wave theory, developed by Louis de Broglie in the 1920s and later revived by David Bohm in the 1950s, offers a deterministic and realistic interpretation of quantum mechanics. It posits the existence of both a wave and a particle. In this view, the wave, described by the wave function, guides the particle's motion. The particle has a definite position and momentum at all times, even when unobserved. The wave function acts as a pilot wave, influencing the particle's trajectory. The pilot wave theory explains the results of quantum experiments, including the two-slit experiment, without the need for wave function collapse or multiple universes. However, it introduces the concept of non-locality, where the wave function can be influenced by distant events instantaneously.